Hey guys, in today's video, I will go through chapter 9 in the book I'm looking at. It's the Alkyne chapter. So all the reactions dealing with alkynes, reduction reactions, the preparation of alkynes, all of that will be covered in today's video. So just to review, we looked at alkanes. So we looked at substitution reactions. That wasn't technically alkanes, but we looked at substitution reactions. We looked at addition reactions with alkenes, and now we're on alkynes, which are triple bond reactions. So first question you should ask yourself is how do we prepare these alkynes just from regular hydrocarbon chains, maybe with a halogen or two, and this is how we do it. We have two halogens right here at the end of a hydrocarbon chain, and you keep the same amount of carbons, right? You keep 1, 2, 3 carbons, 1, 2, 3 carbons. So you keep the same amount of carbons, but you take away those halogens, and in place you get a triple bond. So these are the reagents you use: excess Na, NH2, and H2O, and that will give you that triple bond. And that excess is important because that takes away both of those halogens, and you end up with that triple bond. And I wrote right here, remember to keep track of your carbons because that's super important. You should have the same amount of carbons that you do at your reactants that you have at your product. So that's very important. So one example I have here is this reaction, and I'm gonna number the carbons right away just so I make sure that in my product, when I go through this reaction, I end up with the same amount as well. So we have, instead of bromines, we have 2 chlorines, and the reagents are excess Na, NH2, and H2O. So let me write the same amount of carbons, 1, 2, 3, 4, and 5. So these chlorines are where your triple bond will end up between the 4th and 5th carbon. So that's the first reaction. And that's pretty straightforward. So that's how we synthesize and get to a triple bond. If you only have one halogen, you don't use excess Na, NH2, and H2O. You can use this reagent. This is taking a strong base in this reagent right here, and you get a negative charge from it, so you can take out, in this case, it's a primary halogen, and replace it with a double bond. So this does, where we had 1, 2, 3 carbons, we have 1, 2, 3, 4 carbons that we end up with, because we're adding these carbons right here. So you should get more carbons in your product than you did in your reactant. So that's that reaction. And yep. So how do we reduce alkynes? And if you watched my alkene video and the reactions with that, you'll see that this reagent is the same reagent that we use to reduce alkenes to alkanes. And we can do the same thing where we reduce alkynes to alkanes. So we can use H2PT and reduce that triple bond into a single bond, into an sp3 hybridized bond. So again, we keep the same amount of carbons, 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons. Our carbons stay the same. We're just reducing that triple bond, and it doesn't even go to an alkene. It just goes straight to that alkane. So we will have reactions where we reduce that alkyne to that alkene, but this one goes straight from alkyne to alkane. All right, but just like I kind of teased, how do we go from alkyne to alkene? We can use two different products, or I'm sorry, 2 different reagents. And again, I write up here that it's helpful to count your carbons, especially for this one, because even though the orientation of your carbons are different, they're still the same number, if that makes sense. So this first one right here is how you get a cis alkene. and that is using H2 and Lindlar's catalyst. So you can also abbreviate Lindlar's catalyst to Lind-Cat. I've seen that before. And that's how you get a cis alkene. And this is really important for synthesis. And remember, cis is the same side, so you can remember it as same side with those Z's. So this would be the Z isomer. So if that helps you out, that's how I kind of remember it. And then if you use NaNH3 liquid, you can get a trans alkene. So remember, this one's going down from the double bond, and this one's going up. That's why it's trans. So you can get two different isomers from these two different reagents. And usually it's shown like this. You can also write it on the arrow as NaNH3 liquid. I've just seen it shown like this a little more, so that's why I wrote it like that. So those are the two different reagents you can use. The question that I have for those reagents is, what reagent would you use to achieve this following reaction? So what do you guys think? I'll give you a few seconds. So we have a triple bond going into a double bond, so we have to use one of our two that we just learned. This is a cis, because these are both coming down. So we're going to use that first one. We're going to use H2 Lindlar's, I'll just abbreviate it, Lindlar's catalyst. So we're going to use that reagent because we have a cis alkene on that side, on the product side. So those are those reagents. This is a summary of what we just learned. So when you use NaNH3 liquid or H2 Lindlar's catalyst, you can further reduce it to an alkane by using that H2PT. Remember, we've used that for the alkene chapter, and now we're using for the alkyne chapter. So you'll see that a lot, and that's how you can reduce it if you have that double bond and you want it as a single bond. So those are those reagents, and that's how reduction occurs with these alkynes. Moving on to hydrohalogenation. You can see a key word in this is halogen, hydrohalogenation. So this is how you go from, how we just had those bromines and we got them into triple bonds. That's doing the reverse thing. So we're starting with a triple bond and we're ending up with two halogens. In this case, we use excess to get two halogens and excess HBr. You could do excess HCl if you wanted chlorines. So this is really helpful if you're trying to get halogens and your starting material is a triple bond. And remember, we're keeping the same amount of carbons. We have 4 carbons at the start, and we end up with 4 carbons in our product. All right, hydration of alkenes, so getting some oxygens in there, is as some simple products. You start with a triple bond like we have been looking at, and you get H2SO4, comma H2O and HgSO4. Now those are interchangeable. You can write HgSO4, H2O, and then write H2SO4. So you could do it that way as well. You would get the same thing in the product. And they all occur in one step. And you end up with a ketone. This is called a ketone. So you have that oxygen double bonded to that carbon. And pay attention to which carbon that oxygen goes to. We have 1, 2, 3, 4. So this ends up on the 3rd carbon. So it's the first one in that triple bond. So it shouldn't be over here. It should end up just before that 4th carbon there. So it's really important to know which carbons that ketone ends up. Because just like anything in this chapter, you really want to count those carbons. So this example I have here uses that reagent, just a different structure. So let's see what we would get as a product. Again, I'm going to start counting my carbons from here. So we have 1, 2, 3 coming out there. So that is 3 carbons, and the second carbon would get that ketone. All right, so that's how to get a ketone from this. And when we go on into that alcohol chapter, we'll know how to go from a ketone to an alcohol, but that's not covered in this chapter. But this is a really important step in synthesis as well. All right, hydroboration, oxidation of alkynes. So we looked at hydroboration, oxidation of alkenes. This is of alkynes. So we use this complicated reagent, and this might be hard for some of you guys to memorize. It was for me. We use R2BH, H2O2, NaOH. So that, remember, this R2 can be anything. That R can be any compound. So when you see an exam and you see something other than R2, don't be afraid. That can symbolize anything. But what do we get here? This isn't a ketone because we have this hydrogen right here. What that hydrogen symbolizes that this is actually an aldehyde. So ketones and aldehydes, they're different. We have that terminal hydrogen at the end. That's not a carbon, that's just one singular hydrogen. So this is how you get an aldehyde from this. And remember to count your carbons. It was 1, 2, 3, 4 carbons, and we have 1, 2, 3, 4 in our product. So for this example right here, and it says you can also use what we used for our alkene to get a similar product, although you might see this R2BH more than you will that BH3 times THF. You just might see it more. But our secondary step remains the same as H2O2 and NaOH. So using this reactant, what would we get as a product on this side? I'll write out all these carbons, and I'll start numbering from 1, 2, 3, 4, 5, 6. So we should have 1, 2, 3, 4, 5, 6. And this should be our hydrogen, so 5, 6. And we get our double bonded oxygen up here, or down there, I guess I should say. And that is our product. Let me show it without those numbers, so it's easier to see. Everything else stays the same. All right, so don't be afraid that I added this other line here, because you might think, oh, that's another carbon. I'm adding too many carbons. No, that's just a single bonded hydrogen at the end there. Okay. Ozonolysis. So we saw this with alkenes, where we had a double bond and we used O3 DMS, or you could use H2O, and we get something like this, where we have a double bond on each side of this this double bond. We end up with a ketone and two ketones. For alkynes, we end up with carboxylic acid. So we end up with, we're still doing the same thing where we split that triple bond, but we end up with this OH at the end, this alcohol group connected to this double bonded oxygen, and we get that on both sides. So that is what you get when you use O3H2O. So I wrote here, imagine slicing the triple bond into two, and this asks, what about terminal alkynes? What would happen there? So let's say we split this. What would happen? We have an R and then a C. That has to be an H on the other side. Or I'm sorry, that has to be an OH on the other side. And then on the other side, so this right side, we have a CH, OH, oxygen. So that would be, if you had a terminal alkyne, that's what it would look like. That R, again, can symbol anything. So that's ozonolysis. So you can see there's similar names to these alkene and alkyne chapter. They just do different things. So alkylation of terminal alkynes. So how can you add more carbons to your triple bond? You can see we use this reagent for our first reaction. We use it excess NaNH2 in addition to, what was the other secondary step we used here? We use H2O as well as a secondary step. Just making sure I got it. We use that to get to a triple bond, but instead of using H2O as our secondary step, we're going to use something like this to add more carbon. So that we're just, in this example, we're using, this is an ethyl group connected to a halogen in order to connect more carbons into our chain. So this is really important for synthesis problems, because you'll wonder why, oh, how did this get more carbons if it only started with 4 carbons and we have 6 carbons? Well, you can use this step to add more carbons into your chain. Let's see. This is for secondary steps. Say we have hydrogens at the end of our chain. This one isn't just a singular hydrogen at the end of your chain. But let's say we wanted to add, add carbons to both ends of our chain. So let's say we had something like this. For this example, we started with this, and we wanted to add NaNH2 and CH3I. So that would add a methyl group. You would add a methyl to that end. But what about the other end? Well, we can do the same thing as it shows up there, and we can do NaNH2. And we can add, let's say, an ethyl group to the other side. So you can see you can add to both ends, and that's what it's showing in this reaction right here. You can add to both ends. All right, so moving on to this example, it's just a more complicated thing that I already kind of said. We have a triple bond, and we want to add these 2 things to it. And it says the nomenclature right there, if you guys are curious. How do we do that? Well, we can only add one at a time, one side at a time. So let's add this first side first, so we get 2 carbons on that side. So we're adding an ethyl group. So that gives us the ethyl group. And then we want to add 1, 2, 3, 4, 5, and then a methyl right there. So we can actually just draw that. So we can do, let's see, that would be how many carbons in total? 1, 2, 3, 4. 1, 2, 3, 4, 5. I believe that's correct. And then obviously the NaNH2. So on your product, to get that product that we're looking for, we should have 1, 2, 3, 4. Is that the same amount of carbons? 1, 2, 3, 4, 5. Whoops, did I count too much? 1, 2, 3, 4, 5, 6, 7. I think I messed up on a carbon. I think there should be one more here. Let me just redraw that. One, 2, 3, 4. 2, 3, 4, 5, 6, 7. There we go. Something like that. It's not the same as this because I started my triple bond going up instead of, it's shown as down right here, which probably wasn't smart to do, but that's how you would get that for an answer. All right, and that's pretty much all the reactions of alkynes. In my next video, I'll actually be going over synthesis and multi-step synthesis and putting this all together. So feel free to watch my next video. Have a good day, guys.